Só passar mais um exercício ainda em relação à aula de ontem. Então, seja B um monoide. Sorry. Let B be the monoid generated by a certain family of matrices. If some AI is either hyperbolic, so this is in dimension 2. If is either hyperbolic or parabolic, then B is pinching. So this is the first part of the exercise, and the second part is B may be pinching even if every AI is elliptic. So I'm trying to convince you that it's very easy to get pinching. Maybe I should tell you exactly what I mean by parabolic. If you have a non-invertible matrix in dimension 2, hyperbolic means 2 real eigenvalues distinct. Parabolic means 1 real eigenvalue with multiplicity 2. Eigenspace being one-dimensional. The elliptic means 2 complex eigenvalues. Okay, so that's the definition for the purpose of this exercise. Not all matrices belong to these 3 groups. The ones that I'm not including here are the multiples of the identity, which have 1 real eigenvalue, and the eigenspace is 2-dimensional. But, I mean, I'm not interested in those. Okay. So what I want to do today is to generalize the setting that we considered yesterday. I want to introduce a class of objects that we call linear cocycles, because a good part of the course will be around this notion. And I want to explain both that this includes the setting that I introduced yesterday, the setting of random products of matrices, but it includes other situations which can be treated together in many respects. So a linear cocycle has two objects. We are given a dynamical system, which I will most of the times take to be a discrete time dynamical system, given a transformation. One can define linear cocycles with continuous time as well, but doesn't change much. So this is one of the data, and the other data is a function from M to the space of matrices, the space of D by D invertible matrices. A function with values in the space of D by D invertible matrices. And then, given these two data, we define a new transformation, F, capital F, in the product space that acts as a skew product so we just use F in the first coordinate, and in the second coordinate we use A. And this is the linear cocycle. Linear cocycle defined by A over F. Okay. Observe that if you iterate twice, so what you're doing is f of x, f of x, if you iterate twice, you are calculating this, which, using the definition again, is second iterate of f here, and then here is A of f of x applied to the vector A of x, f. Okay? And more generally, f n of x v is f n of x, and then here you have the product, this is v, v ax a f of x a f n minus 1 of x. Okay? And to simplify the notation, we just call this a n of x. So we have this formula for all n positive. Now, if f is invertible, then capital F is also invertible. It's just a matter of checking that f minus 1 of x v is f minus 1 of x. And then one has to think a little bit. Maybe it's useful if I draw a picture. You have x, this is Rd. You have f minus 1 of x. And we want to define So our f minus 1 is mapping this to here. We want to define what we should have, what dynamics should be here. And it's more or less clear that it should be the inverse of the one we have going forward, which is a of f minus 1 of x. So this should be a of f minus 1 of x inverse. Okay? And again, to simplify our notation, we call this a minus 1 of x. The good way to keep track of these notions is to think of the chain rule, the derivative, the rules for the derivative, which are exactly the same here. So in general, f minus n of x, v, is f minus 1, f minus n of x, a minus n of x, applied to v, where a minus n is, and now I have to think, is a f minus n of x, a f minus 1 of x inverse. You just take this expression. It makes sense because all the matrices are supposed to be invertible. Take this expression and check that this is the inverse of this. Just compose them and you see you got the identity. Okay. So most of the time we will be talking about this kind of object. And I want to convince you that there are different examples of this object. I'm going to introduce 3. But there are many situations in various parts of mathematics, physics, biology, economics, where you find this kind of object. So the first example is the situation that we looked at yesterday. So the first example is products of random matrices. So remember, I started with some certain number of matrices and certain probabilities. And we were looking at random variables given by obtained by multiplying random choices of matrices in this set according to this probability. So this was the model that we had yesterday. I'm going to explain how you can realize it with this language. So take X to be the set of matrices. Then take M, this M here, to be the set of sequences in X. Okay? Now I have to tell you who is my transformation. What is the transformation that is involved here? Well, the transformation in M is the shift. The shift is just a map that takes a sequence alpha 0, alpha 1, alpha n, etc., and maps it to, it moves everyone to the left and drops the first one. So alpha 1, alpha n, etc. That's my transformation. Now I also have to tell you U is with the function A that I want to consider. Sheesh. So take this F and take A. So A is a map from M to GLD. It starts with a sequence. And I choose A to be the projection on the 0th coordinates. Alpha 0. Okay? So the cocycle is the linear cocycle associated to this data, takes a sequence, alpha n, and a vector, and maps it to the shift, alpha n plus 1. Okay, this is the variable x in this case. And then I have to calculate A of x and apply it to V. A of x is A of the sequence, which is alpha 0, applied to V. Okay. So you use alpha 0 to iterate your vector, and you drop it from here. If you do this n times, then, or k times, then you are going to, according to the formula that I already erased, you will have to iterate k times here. So n plus k. And then the first time you use alpha 0, the second time you use alpha 1, which is the first coordinate here, and so on. So you have alpha 0, alpha 1, alpha k minus 1 applied to V. Okay? So you see that what you're getting here are the possible values of Bn. Bn is formed by these products. B1 corresponds to alpha 0. This corresponds to alpha n minus 1. And these are the possible values of the sequence Bn. Okay? So I'm not proving anything at this point. I'm just saying that you can write this game of multiplying random matrices. You can formulate it as a linear cocycle with these data, F and A, and it's essentially the same object. Okay? The second example is, in a sense, closer to our experience. And I'm going to refer to it as derivative cocycles. It goes like this. Take M to be a torus, TD. Not D, TM. Any torus. And F from M to M to be a local diffeomorphism. So the map is not necessarily injective, but the derivative exists and is an isomorphism at every point. Then you can define the following transformation, the following function. A is also known as the derivative of f, is a map from M to sorry, I should have said the d-dimensional torus. Yes, I do want to be the d-dimensional torus. So at each point x in M in the torus, I consider the derivative of f. And I'm going to call this A of x. So what is the derivative of a diffeomorphism? It's a map from the tangent space to the tangent space at the image. And if you have a torus, and since I'm assuming this is a local diffeomorphism, this is invertible. This is an isomorphism. Since you have a torus with dimension d, the tangent space is just Rd, and the tangent space at the image is Rd. Okay? So, what this means is that A is a function. A is a function from the torus to the space of invertible linear invertible transformations from Rd to Rd, which is just GLD. Okay? So you can consider the corresponding cocycle. The linear cocycle associated is the map F from M to Rd, M to Rd, that sends xv to f of x df of x v. Okay? And if you iterate n times, you get this map here. You just have to look at the formula that I gave you for Fn, and you will see that it was designed in such a way that when you iterate n times, you are actually getting the derivative. That's in the definition, I copied the chain rule, and so it fits precisely with this. By the way, that's the reason why I told you last time that we multiply by starting with B1 on the right and we go to the left. We could do the theory the other way around, but then it would not, this formula would be wrong. Okay? And it doesn't, there's nothing special about the dual theory, just the same theory, except that we are used to multiplying things in this way. Okay? Now, a question. So that's why we call this a derivative cocycle. I'm saying that every time you have a smooth map on a manifold, there is a linear cocycle associated to it. Question. Where did I use the fact that M is the torus? Here. I said the tangent space is Rd. Now this is tricky, because when you have a manifold, in general, for instance, a surface, if M is a manifold of dimension d, then the tangent space at any point is a vector space of dimension D. And so, you know that all vector spaces with the same dimension are isomorphic. And so, Txm is isomorphic to Rd. However, there is no, in general, there's no natural, no canonical choice of an isomorphism. There's no rule for choosing one isomorphism or the other. And here we need such a rule, because if I identify Tx of m with Rd in a way, and I identify the tangent space at the image in a different way, if I change the isomorphisms, the map, the matrix that I get changes. So in order to have A well-defined as A of x well-defined as a matrix, I have to say what is the isomorphism that I use to identify the tangent space to Rd. Okay? In the torus, that's not a problem. In the torus, we can say that in my isomorphism, this vector will be mapped to the x-axis, and this one will be mapped to the y-axis. In the torus, the tangent space is canonically identified with Rd, but not in general. Okay? So in general, we don't have, for general matrices, for general manifolds, A of x, the derivative, cannot be seen as a matrix, as a matrix. There's no canonical choice of a basis. When you go from a linear map to a matrix, you have to choose a basis. In the torus, there's a canonical choice of a basis, but not in general manifolds. For example, not in the sphere. So there's a definition. M is parallelizable. A manifold is parallelizable if there exists continuous vector fields x1 through xd. D is the dimension, a d-dimensional manifold M is parallelizable if there exist continuous vector fields such that the value of these vector fields defines a basis for the tangent space at every x. The torus is parallelizable. The sphere is not. If your manifold is parallelizable, you can do what I did there. Otherwise, you cannot. Now, we shouldn't be too depressed by that. This does not mean that for general manifolds we cannot play this game. Just one observation: if M is parallelizable, the tangent bundle Tm can be written as a product. And that's precisely what happens here. This works because for the torus, the tangent bundle is the product of M by Rd. In general, we cannot do that, but we can do the obvious thing, which is to think of the derivative as acting. In general, the derivative acts on the tangent bundle, which is not a product. So Tm to Tm, what it does is it takes xv into f of x df of xv, and we can call this a linear cocycle as well. This can also be called a linear cocycle. F. What I'm saying is that my definition of linear cocycle requires the ambient space to be a product, but I could generalize the notion to include examples such as this, where the product is not, where the ambient is not a product, is a fiber bundle, is a vector bundle over M.
If we have a compact space and we just embed in some high-dimensional real.
There are various reasons why I said I could do that. There are various reasons why I'm not going to do that. Because from our point of view, I mean, from the point of view of topology and so on, it's completely different. Okay? But from our point of view, it doesn't make much difference. We don't gain anything by looking at more general linear cocycles. And so, for the purpose of the course, a linear cocycle is a skew product on a product space. Okay? But I don't want you to feel that the sphere doesn't belong to our game. We could easily include all manifolds in this setup. Okay, one third example. It comes from a completely different direction. Now, all three come from different directions. First one is from probability theory, stochastic process. The second one from smooth dynamics. And the third one from spectral theory. These are called Schrödinger cocycles. The connection to Schrödinger is as follows. Schrödinger equation is an equation in quantum mechanics. It's a partial differential equation with 4 variables, 3 space variables, 1 and plus time, 4 variables. And it's amazingly complicated. So what people try to do to get rigorous... Estão todos ruins aqui, né? O crampo está arranhando. What people, I mean, the physicists have a good intuition of what the Schrödinger equation says, but if you want to try to make it rigorous, it's very hard. So what people do is to simplify the Schrödinger equation. The simplification is outrageous, but that's what they do. First of all, you look at the stationary differential equation, where time doesn't exist. So you only have 3 space variables. Then 3 is too much. You take only 1 space variable. So instead of a PDE, now you have an ODE with only 1 variable. And then an ODE is still too complicated because time is continuous. You take the discrete time version, you discretize time, and you end up with something. And then you try to study that something and try to get conclusions. There's a huge theory about this. I'm making a little bit of, introducing a little bit of humor, but there's a huge theory to study even this very, very simplified equation. So let me tell you what that has to do with cocycles. So we take L2, the usual space of sequences such that the sum of the squares is finite. This is little L2. And then we take an operator, a linear operator on L2. H in classical mechanics is always used to represent energy. Energy or the Hamiltonian. In quantum mechanics, things that are numbers in classical mechanics become linear operators in quantum mechanics. So H is the energy associated to the atomic system that you want to study. And H is defined as follows. You take a sequence, I'm going to use U here, it's the notation that is in the book. You take a sequence UN and you map it to the sequence UN plus 1 plus UN minus 1 plus VN UN. We use sequences that are bilateral, okay, indexed by Z. So this is the Schrödinger operator associated to the sequence Vn, capital Vn, and this sequence is called a potential. The reason being that in the physical context, this is the potential energy. Okay? What does... I don't think I write down the... Well, I do. Okay, so we'll see. So this is a Schrödinger operator. And, there's a data here. There's some data that is given, this potential here. And in fact, there are different problems depending on how you get this potential. There are at least two important classes of Schrödinger cocycles: random Schrödinger and quasi-periodic Schrödinger. That depends, the difference has to do with how you obtain Vn. So in random Schrödinger, the Vn are random variables. So in random Schrödinger, you consider a shift space F from M to M, the shift map, the same as I introduced before, just the map that shifts the sequences to the left. And then you take some function V from M to R, choose some x in M. And then you define Vn to be V calculated at Fn of x. That's one way. I mean, you can play with whatever sequence you like. I'm just telling you the two types of constructions that people like the most. Yes? It's a point in M. Oh, any set. Any set. Just take a space of sequences. This is just any set. Typically, it's a finite set, but that's not very important. Quasi-periodic is perhaps the most famous because it involves a lot of beautiful mathematics, is where you take M to be the circle. In fact, you can do this with, well, here I actually wrote the torus, more general. F from the torus to the torus is an irrational rotation. You can think of the case d equals 1, because in fact 90% of the papers are about the case d equals 1, which is hard enough. And take some function, v as before from Td to R, choose some x in Td, and then define Vn as V of Fn of x. And in fact, for many, many years, essentially all the papers were about d equals 1 and v is the cosine function. Now there's a much more global theory, but okay. So, but I mean, I'm not going to use this. I'm just telling you what are the two more popular constructions of the sequence Vn. Let's go back to this. So what kind of things do we want to know about H, about this? About this linear operator? Well, one of the things that is important for solving the Schrödinger equation is to understand what are the eigenvalues of H. And that's where we get to spectral theory. We want to understand what is the spectrum of this operator. Turns out, and that's not an easy, that's theorem, that if you know the spectrum of this operator, then you are halfway into solving the Schrödinger equation. Well, so this is just the usual eigenvalue equation, except that we have to respect traditions. And tradition is that in this context, the eigenvalue is denoted by E, because it's an energy. Okay? So we would like to understand this equation, the eigenvalue, eigenvector equation. And this is something that you find in, especially in this case, you can find in books in ODE. For example, the book of Hartmann has a discussion of in continuous time of order 2 differential equations, order 2 differential operators, and this is a discrete version of that. Now, this equation can be. So you see, we are doing analysis at this point. We are trying to find the eigenvalues and eigenvectors of a certain linear operator in the Banach space, L2, in the Hilbert space. Now, this equation can be rewritten in coordinates, and if you do that, you have the expression of H. It says that UN plus 1 plus UN minus 1 plus V of n UN equals E of UN, right, for all n. And this is an order 2. These are not called differential equations because the time is discrete. They are called difference equations. This is an order 2, second order difference equation. Why second order? Because it involves terms of the sequence from n minus 1 to n plus 1. The difference here is 2. Okay, it also involves UN, that is in between. And when you have a second order differential equation, you can always transform it into a first order differential equation. That's this trick. If you have x second derivative equals f of x, you can transform this into a first order equation by using this trick. You call x dot, you give it a name, ui, you call it y, and then x double dot becomes y dot equal f of x. Second order differential equation becomes a first order system of differential equations. You can do that also in discrete time. That's what I'm going to do. So how does that go? You give a name to UN plus 1. You call UN plus 1, you call Vn. Just like here, x dot you call y. And when you do that, you get the following two relations. UN plus 1 equals Vn do I want to write it like that? Sorry, yeah. Okay, let me write it. Okay, first, before that, let me rewrite this as follows. UN plus 1 equals, I'm going to move everything to the second term, equals E minus Vn UN minus UN minus 1. Okay? And now, with this change of, with this new variable, I can write the equations as follows. Vn Vn equals E minus Vn minus 1 minus UN minus 1. UN equals Vn minus 1. Okay? So what did I do? Here I wrote Vn. Here I wrote un Vn minus 1. Okay, this is for all n. Okay, let me say it this way. Let me write it this way. I call un, I call Vn minus 1. Maybe it's easier to follow. It's the same thing. So here where I had un, I write Vn minus 1. This is this relation that I'm rewriting here. And here I have un plus 1 equals Vn. Okay? Of course, this is just a manipulation, but it's a useful manipulation. I'm not doing this for the pleasure of manipulating the expression. This is useful. This expression can be written as follows. Vn un equals E minus Vn minus 1, 1, 0 for all n. In other words, the solutions of this correspond to the trajectories of this transformation here. Correspond to the trajectories of this. You see, I'm telling you how to, given a pair Vn minus 1, un minus 1, to get a new one. This is an iteration. And this is given by a linear cocycle. Is a linear cocycle. Namely, so I'm going to look at the two cases that I'm more interested in, that we are more interested in. So F will be either the shift or rational rotation. So namely this following cocycle. F on M cross R2. R2 because my matrices are 2 by 2. Defined by X, and then a vector in R2 I represent as VU goes to f of x, and then the matrix, I'm going to write it in color, E minus V of Fn of x minus 1, 1, 0 applied to UV. Okay, this is this matrix here. It appears here. So maybe you are not impressed by what I achieved here. I started with an equation, but I want you to be impressed. I started with an equation in spectral theory. We want to find the eigenvalues of this linear operator and the eigenvectors. And I told you that if you want to find, say, the eigenvectors, that's the same thing as calculating the trajectories given by this iterating procedure, which is just this linear cocycle. When I say corresponds, I was careful here because solutions of this are sequences UN. And here you have pairs, UN, VN. Okay? But you also have the dictionary. Dictionary is this. VN is just the shift of UN. Okay? Okay, and then why is this useful? I'm going to give you one example, one kind of statement where one can use the theory of linear cocycles that we are going to develop to say things about the spectral theory. So claim, and this will become more clear in the future, but claim. First of all, observe that these matrices have determinant 1, right? These are in SL2. 2 by 2 matrices with determinant 1. So the Lyapunov exponents lambda plus and lambda minus for this cocycle are symmetric to each other. Okay? So my claim, and this will become obvious in a few days, if the Lyapunov exponents are different from 0, then star has no solutions. So, using the methods that we are going to develop to study linear cocycles, if we are able to prove that the exponents are different from 0, then there are no solutions to this equation. Let's keep in mind that there is a parameter here, which is the energy. Okay, so this depends on which energy we are looking at. Now, why is so? In a few words, it goes like this. If lambda plus is positive, then some vector, some direction has to grow because the norm is growing exponentially fast. Okay? On the other hand, this also implies that lambda minus is negative. So there's some other vector, not necessarily orthogonal, such that by iteration in the future is going to contract. And so by iteration in the past is going to expand. To the past is going to expand. We are in an invertible situation. Time can be inverted. So lambda plus positive, lambda minus negative means that we have a kind of saddle behavior where in a certain direction vectors have to grow in the future, the other direction have to grow in the past. So all vectors have to grow either in the future or in the past. Is this clear? It's like looking at a linear map, say 2001 half. Okay, this is A. I'm saying A n of V norm goes to infinity for every V, either when n goes to plus infinity or when n goes to minus infinity. Everyone agrees with this statement? For horizontal vectors, you iterate forward, and this 2 means that the norm is going to grow. For vertical vectors, you iterate backwards. And what about the other vectors? you can iterate both forwards or backwards, right? So for a map like this, all the orbits are unbounded. Actually, most are unbounded in the future and in the past. Some are just unbounded in the future, and some are just unbounded in the past. So if you have lambda plus and lambda minus different from 0, something very similar happens here. All trajectories of this linear co-cycle have to go to infinity in the future or in the past. But sequences in LD don't go to infinity. In L2. Sequences in L2 don't go to infinity. Okay? Maybe I should, to be more precise, say has no solutions in L2. Okay? This was a intuitive explanation, but as we become more familiar with these notions, this will become essentially, there's no proof. Essentially what I said is a proof, but we have to become more mature about these objects. Okay? So this is just to explain how linear co-cycles and the theory that we want to develop can help in other parts of the world, in other parts of mathematics. Okay. Any questions so far?
So we can construct trajectory for each energy, right?
For each energy, we have a different linear co-cycle, Fe, with different trajectories, and whether the exponents are 0 or not depends on the energy. Okay? The spectrum of the Schrödinger operator corresponds essentially, it's not exactly the same thing, but corresponds essentially to the values of the energy for which the exponents vanish. Okay? I've observed that the set of eigenvalues for the Schrödinger operator is contained in the set of energies for which the exponents are 0. And they are essentially the same thing up to taking closures and things like that.
A equação de Schrödinger em R3 cartesiano tem, quando o potencial é pequeno, tem uma solução. Esse método de discretização com que se está fazendo, no caso você está tentando estudar, dado a energia, se tem ou não solução. Quando tem solução, a energia passa a ser um alto valor do operador. Isso corresponde. Eu quero saber a relação disso com a teoria.
Com a teoria quântica.
Isso.
So his question is what's the relation between all this and quantum mechanics? What does this have to do with solving the Schrödinger equation? Essentially, the Schrödinger equation, the discrete stationary Schrödinger equation is this equation. Okay? And so we are trying to find the solutions. Now, one important part of the problem of solving an equation is to say what is the domain of the equation. Okay? So the answer depends on the domain. I've chosen I've chosen as the domain L2, which means that I'm looking for solutions that go to 0 with a certain rate as your n goes to plus infinity or minus infinity. Okay? So this really has to do with knowing when does the one-dimensional stationary discrete Schrödinger equation have a solution of that type. Why do we choose L2? First of all, because from the mathematical point of view, this is a very nice space, it's a Hilbert space, and so on. But that's not the only reason. Another reason is that the physicists are very interested in the phenomenon they call localization. Localization in physics means, quantum particles are not really objects, are not really solid objects. They don't have a well-defined place. You cannot say electron number 17 is here because of the uncertainty principle. Any particle is essentially anywhere in the universe. But if you are able to say that it is most likely in a certain region, then you speak of localization. When you localize your particle. So one thing that interests the physics very much is whether the Schrödinger equation has localized solutions. Completely localized would be a Dirac mass, but that doesn't exist in quantum mechanics. This is what you can expect. So I'm trying to answer your question. All this is simplified models to the actual Schrödinger equation, but it really has to do, this equation formulated on L2 is really about knowing whether the one-dimensional discrete time stationary Schrödinger equation has localized solutions. Okay? The model is simple, but the question is the kind of relevant question that the physicists want to ask. But I'm not an expert on this. I'm just trying to stress the why it's useful to have these manipulations and in which way dynamics and the ergodic theory can help in that. Okay. Now, I'm going to spend a little bit of time talking about one special class of cocycles that are called hyperbolic or uniformly hyperbolic cocycles. These are probably familiar to those with a little bit of culture in dynamics, but let me maybe spend the rest of the class today talking about that case. In a sense, I'm giving a fourth example, except that it's a large class of examples, and not only it's large, it's a model for an even larger class of examples. So, in this context, I'm going to suppose that I'm going to suppose that M is a compact metric space. And F is a homeomorphism. So A from M to GLD is continuous. And then the main assumption is that there exists subspaces EU of X and ES of X contained in RD. This is for every X in M. So these two subspaces are transverse. And satisfy a certain number of conditions. first condition is called invariance. And invariance means that A of x applied to E EU of x is equal to EU f of x. And the same thing is true for ES. Okay? So this is telling you that at each point you have a direct sum with the sum being RD, and your matrix at that point, A of x, preserves this decomposition, meaning that it sends this vector, this subspace, into the corresponding subspace at f of x, and this one just the same. Okay. That's the first condition. The second condition is called hyperbolicity. And it says that there exists constants c and lambda such that a n of x restricted to e s x is in norm is less than c lambda n. So what does this mean? When n is large, lambda n is very small because lambda is smaller than 1. So the product c by lambda n is very small. So the whole point is that this is larger than 1 for n large, smaller than 1 for n large. And so this norm is smaller than 1, which means that the matrix contracts all the vectors. And then we have a dual condition for EU. But I'm not going to say that the norm is small because is large, because saying that the norm is large doesn't say much. I'm going to say that the conorm is small. The norm of the inverse is small. And the point is that this is for every n and an x. Example. Just take f from the 2 torus to the 2 torus given by xy goes to 2, 1, 1, 1 times xy. Actually, I didn't recall what the torus is. For me, the torus is always RD quotient ZD. So the torus is just like RD, except that you identify x1, xd is identified with y1, yd if the difference xj minus yj is an integer. Okay, that's what this means. It's formed by d upples, identified by this relation. Any two vectors whose difference is an integer vector are identified. So I have the right to represent the elements of the torus as pairs of real numbers and to define f in this way. So if you take this, then df, the derivative cocycle, is hyperbolic, is uniformly hyperbolic. And this is an exercise. And it's an easy exercise. The reason it is easy is that when you want to prove that a certain cocycle is hyperbolic, the main difficulty is that the definition says there exist subspaces. The main difficulty is to find these subspaces. Okay? They are not really subspaces, they are fields of subspaces because they depend on X. Okay? So the difficulty for proving hyperbolicity, if you don't have any tools, is that you probably don't know where the subspaces are. But in this case you do. In this example you do. Because this is a hyperbolic matrix. Hyperbolic matrix. It has two eigenspaces. E1 and E2. And you can use them to define the EU and the ES here. Now I want to say, I'm not going to do all details, but I want to say something about some properties of hyperbolic cocycles, especially in the two-dimensional case. I'm going to state a proposition that I will not prove, because later on I will use the same argument to prove something different. So I might as well do it later. But from that proposition we are going to deduce some consequences for continuous for uniformly hyperbolic cocycles. So take the dimension to be 2, then the cocycle is hyperbolic if and only if the norm goes to infinity when n goes to infinity. I'm missing some hypothesis. Yeah. Yeah, no, this is not correct as it is. So suppose A goes from M to SL2. So 2 by 2, but I also want the determinant to I also want the determinant to be 1. And then I want to say that AN goes to infinity exponentially fast. The way to say that, if there exists constants C and sigma such that the norm of an of x is bigger than C sigma n for every n and every x. This is a low-dimensional statement. This is not true in higher dimensions. It's only for the surface case, for the two-dimensional case. But it's a very nice and useful criterion for hyperbolicity. This allows us to prove hyperbolicity without having to know where the subspaces are. You just have to take the iterates and see that the norm of the iterates grows. You don't even have to iterate backwards. It's enough to iterate forward. And if this grows exponentially fast for every n and every x uniformly, the constants C and sigma are independent of n and x. That's why we say uniformly hyperbolic. Then this suffices to get hyperbolicity. So I said I'm not going. The proposition is proved in the text. I'm not going to prove it here because we will be using a similar argument at some point, and I don't want to repeat. Okay, so this has some consequences, and that's the consequences that I want to talk about. One consequence is given by this proposition. Suppose that the cocycle defined by A over A over F is hyperbolic. So let F be fixed. And suppose you have a function A with values in 2 by 2 matrices such that the corresponding cocycle over this F is hyperbolic. Then the cocycle defined by B over F is also hyperbolic. For any B in a small, in the neighborhood of A. So being hyperbolic, yes? Diga. I mean uniformly hyperbolic, yeah. Yeah, in the book I don't say uniformly at all, but so it's always in this setting. So in order to speak of neighborhood, I have to tell you what the topology is, And it's the topology given by this distance. The distance between A and B is the supremum over all x of the distance between A of x and B of x. D is different D. This is a distance in the space of functions, and this is a distance in the space of matrices. Of course, I didn't define the distance in the space of matrix either, so let me do that. The distance between two matrices is, well, the norm of the difference. In fact, I should this is for alpha and beta in SL in GLD. If I do it in GL, this is not the distance that I want. I want the maximum between alpha minus beta and alpha minus 1, beta minus 1. But in SL, for matrices indeterminate 1, if you control the difference between the matrices, you control the difference between the inverses as well. So we don't, in SL, we don't need a second part. Okay. And here you can use wherever norm you like in the space of matrices. For instance, the operator norm that I defined last time. So by neighborhood, I mean neighborhood in the topology of uniform convergence. Two functions are close if they are uniformly close. Close at every point with uniform estimates. Okay. So this proposition deserves to be called stability. Stability of hyperbolicity. It says that the space, given a certain transformation f, the set of functions, of continuous functions from M to SL2, for which the cocycle is hyperbolic, is an open set. Okay. The way I wrote this proposition, there's more, but let's look at this. Okay, so what is the idea of the proof? So first of all, we look at A, and we have, by assumption, at each point we have this decomposition EUX, ESX. At each point, this corresponds to the point X, satisfying the two conditions that I described here. So let us consider here something that I'm going to call the cone, the unstable cone at x. So what is the unstable cone at x? Is the set of vectors v of the form vu plus vs in exu plus exs. That's what I'm trying to describe here. This is this quadrant here. So it's composed of the vectors v of the form vu plus vs such that vu is bigger than vs. Okay, so geometrically it's this region here where you take any vector that you decompose into the direct sum, and the component that you get along EU is bigger than the component you get along ES. Okay. Now, we know that ANX of VS is smaller than C lambda n Vs, because this is part of the definition of hyperbolicity for every n and every x. And we also know that ANX of VU is bigger. It's the other way around. So it's bigger than C lambda n inverse times VU. It's perhaps easier to understand this if you move this factor to the other side. Okay, when you talk about the unstable, you have to reverse time. Okay, so if you take V in the cone, V inside that cone, ANX V, and you start to iterate. So for any V here, you start to iterate. The iterates are just the sum of VU plus VS. This is a linear map. Now you have a sum. You do something that is always very dangerous, which is to bound from below by the difference. Okay. Why is it? This is dangerous, but I'm not very worried. Why am I not very worried? Because I know that this component that points in the unstable direction, by iteration is going to grow. The other component in the stable direction, by iteration, is going to decrease. So this here is bigger than 1 over C lambda n VU. And this one is smaller than C lambda n Vs. Lambda is a number smaller than 1. So this thing here is very small for n large, which means that this factor is enormous and this is tiny. Okay? So if I put them together, and I remember that I'm looking at vectors that are in the cone, so for which VU is bigger than Vs, I conclude that this is bigger than 1 over C lambda n minus C lambda n times VU. Okay? So this is a positive number. This is very small. This is very small. I still want to do one little extra step. I'm going to say that this is bigger than 1 over c lambda n minus c lambda n v over 2. Why is it that I can do that? Well, because, of course, the norm of V is smaller than the norm of VU plus the norm of VS, which is smaller than 2 times the norm of VU. Okay? So the conclusion is there exists C bigger than 0 and sigma bigger than 1 such that the norm of an xv is bigger than c sigma n norm of v for every x in M, every V in the cone, and every N. So what does, you just choose, if you want, I mean, you just want this to be bigger than C to the sigma n. So you can choose, for example, C equal 1 over lambda, and then C very small, little c very small, for example. Okay, it's just choose the constant sigma and C in such a way that this quotient is bigger than, this expression here is bigger than C to the sigma n. Well, maybe you cannot do it for every n, but for every n large. Okay, as n becomes large, this term here becomes irrelevant because it goes to 0. This is the important one, and well, I could. Let me see how I wrote this. This is a little annoying to say. Okay, I actually wrote something which is nicer, maybe easier to believe. There exists n and n such that this is bigger than 3 or 4 times v for every x and every v. Okay, maybe this way it's easier to believe. I'm just saying that this becomes bigger than 4 if you fix n, and n does not depend on x, and 0 such that this is bigger than. Now, there's another thing that we proved, although I didn't say it, and an of x and 0 of x, v, belongs to the cone of fn0 of x. So I get two properties, A and B. Get two properties, A and B. And the second one actually came for free, because you see, what I have to justify the second part, I have to say that this norm is smaller than this one. Right? Because these are the components, stable and unstable. I have to justify that this is smaller than this. But this is smaller than this. This factor is a small number. Vs is smaller than Vu. Then this is a big factor. And this product is smaller than this. Okay? I started with a vector where the unstable component was big, the stable component is small. And then as I iterate, the unstable becomes even bigger and the stable becomes even smaller. So, of course, I still have this relation. Okay? Now take any B close to A. Uniformly close, that topology. Then the n-zeroth iterate B is close to the n-zeroth iterate of A. When I say close as I like. If I make B very, very close to A, then the 17th iterate of B is close to the 17th iterate of A. I cannot say that all iterates of B are close to all iterates of A, because that's an infinite number of iterates. But if it's one fixed iterate, then I can say it. So that A Bn0xV, well, maybe it's not bigger than 4 times V, but by continuity, by proximity, it's bigger than 2 times V, or 3 times V, for every x. And for every x and V. The matrix AN, the matrix AN0 takes the unit circle, AN0 takes the unit circle and maps it into something which it's certainly an ellipse. What I know is that it's an ellipse that contains the circle of radius 4, because the expansion is bigger than 4. When I replace AN0x by some matrix that is closed, now if I instead of AN0 I do BN0, then I will get a different matrix, a different ellipse, maybe closer to the origin, but certainly not very close to, much closer to the origin. So I get at least a factor 2. Okay. Also, if A sends every cone, every vector in the cone inside this cone, then the same is true for B. Right? This is the time of the lecture where the professor takes advantage of the fact that the audience is tired and starts cheating. No, this is not true. What I just said is not true. The fact that A sends every vector that was in this cone inside the vector, let's see. Property A means that if you start with a vector inside this cone here, cu of x, then the image by A and 0 is also inside the corresponding cone at the point fn0 of x. Okay? But so if now I take the same vector and instead of applying A, I apply B, of course I will get a vector that is close. But that doesn't necessarily mean that it is inside this cone. Because to begin with, maybe this vector was on the boundary. And if it is on the boundary, having another the other image being closed might be outside. Okay? So I have to be a little bit smarter. Let's go back here. I said, let's go back to the proof of B. I said that we started with a vector where Vs is smaller than Vu. Right? Could be equal, but not larger. As we iterate, the S component becomes smaller, strictly smaller. The U component becomes bigger, strictly bigger. So at the end, after n iterates, this one is strictly smaller than this one. So I have much better than what I wrote there. Here I'm only saying that the stable component is less or equal than the other one. But I have much better, and I'm going to stress this by changing the cone. This is a different cone. And what cone is this? C star u of y is the set of vectors v equals vu plus vs, such that vs is not just smaller than vu, it's smaller than 1/4 vu. Okay? And I can do that because I started with Vs less or equal than Vu. Vs becomes, say, twice as small. Vu becomes twice as big. So in the end, this one is 4 times bigger than this one. Okay? So what's the advantage of that? The advantage is that it tells me that if I start with a vector here, any vector here, its image will be contained not only in C, it will be contained in a strictly smaller cone. C star. Okay? This is for A. And now, if B is sufficiently closed, now I no longer have the problem of having vectors on the boundary. If I have a B that is closed, it could move the image. The image could be a little bit further away, but it cannot leave this cone anymore because it is starting from a cone that is sufficiently, strictly smaller. Okay? This is written down in the book. You can check the details, but this is an important part of the proof, important part of the reason why this is true, and so I don't want to give you a false impression. Okay, so we are very, very near the end. What we proved, let me summarize here what we proved. So, we proved that there exists n0 such that, and a neighborhood say V of A, such that B n0 of xv is bigger than 2 times V, and B n0 of xv belongs to the cone at f n0 of x for every x in M, for every V in the cone, and for every B in the neighborhood. Remember, we want to prove that the cocycle associated to B is hyperbolic. Okay? And in order to do that, by the proposition that I just erased, I only have to show that Bn of V, the norm, goes to infinity. So we want to prove this is what we have. And now what we want. We want to prove that Bnxv, Bn norm, grows for every x and every n. And that there exists C and sigma. Okay, this is what we want. I'm going to prove that that is a simple consequence of this. So, given any x, because this has to be proven for every x, take V in the cone. Could be, for example, in EU, doesn't matter, any one in the cone. Then, because of this property, the iterate n0 is bigger than 2 times V. Okay? That's good. I have to prove something for every n. I already have one value of n. Now, what can you say about B2n0 of V? This is the moment where you understand the proof. Unfortunately, the secret is hidden up to this point. This is the moment where you understand why you had to work so hard. Okay, what is B2n0 of x? Is Bn0 of x applied to V, and then what? And then B, another Bn0. Where? At Fn0 of x. Okay? Very good. Bn0 x of V belongs to the unstable cone of Fn0 of x. So, this is bigger than 2 times the norm of Bn0 of xv. Because of this and because of this. We know that vectors in the cone get multiplied by 2. And we also know that at the end, they are still in the cone. And this is bigger than 2 square v. Okay? But see how important it was to know that at the end we are again in the cone, so that we can iterate this procedure. It's not that every vector is expanded. Okay? So once this, I know that you are tired, we are over time already, but think about this. Because that's where the proof makes sense. Okay? The rest is the rest. So this, you repeat this argument, bkn0 of x is v is bigger, is larger than 2 to the k v. Okay? And this is essentially what I wanted. Wait, no, it's not what I wanted, because here is n, and here is n, and here I have kn0, and here I have k. Okay, but that's not a big deal. 2 to the k is also known as 2 to the 1 over n0, n0 to the k. Okay, so this proves the claim, this claim, for n of the form k n0, for multiples of n0, with sigma being 2, 1 over n0. Right? I was able to prove what I wanted, not for every n, but at least for the multiples of n0. And my constant sigma that I was able to obtain was this one. Okay? In general, for general A, for general n, this is very common in hyperbolic dynamics. Once you've proven for multiples of a given number, in general you just divide. Write n as kn0 plus a remainder, and finish the proof. This can take only a finite number of values, and you can absorb that into the constancy. That's what the constant is there for. Okay. Okay. All the details are written down, and that's what I wanted to say. The proposition that is written also says that the subspaces ES, EU, and ES that you get for B are close to the ones that you get for A. So this decomposition varies continuously with the cocycle. Okay, good. That's all for today. See you again on Thursday.